everyone. Today lecture is dual module. So our main focus is dual module, but when you studied the linear algebra, this concept, dual module concept is significantly similar to the dual space of the linear algebra. Today lecture is the focus dual module. In prior to referring to the explaining the dual module, I explained the bimodule concept and then explained the dual module and comparing to the linear algebra. Now let's talk about definition of the R module in order to understand our first focus in the bimodule. When we studied in the module, then this is mostly wrapped R module. Only we deal with this left R module or left module over R. This definition is here. R is a ring and A is additive abelian group goes to the A. Then when we choose the ring element and additive abelian group element goes to RA and satisfies the condition. First, if R and R prime is a ring element and A and A prime is additive abelian group element, then R plus R prime A is RA R prime A and R A plus A prime is RA plus RA prime and also satisfies commutative rules. R prime A is equal to R prime A. Then this satisfies, this condition are satisfied, then A is left R module or A is left module over R. Let's consider in this left and in this case consider the right side R module. So in this case right, but instead switch the notation S module or right module over S. In this case, literally, the notation, the product is switched. So ring comes to the right side and additive abelian group A is to B. For convenience, denoted B goes to, in this case, A, B. Okay. S is a ring, B is additive abelian group. Then we consider BS goes to, in this case, BS. Note that R is the left side, ring at left side in comparison to this left R module, this ring element S is right side. And to consider if the ring S and S prime in S and B prime is B, when the consider the ring condition, but because the ring is located in the right side, to compare it to the first condition, S prime S is right side and B is the ring, B is the additive abelian group. Okay, this is, say, Bs plus Bs prime. And to compare the second, B plus B prime S is equal to Bs plus B prime S. And the last condition, in this case, S prime B is equal to B S prime. B S in B and S in S. So this is also result in B. So this is correspond condition. Then if this condition satisfied, then B is right S module over S. Let's consider RS by module, which literally we can guess work the combination of the left R module and the right module. Left module and right module. Definition: an abelian group A is an RS by module provided A is both left R module and right R module, but this is not sufficient. Another condition is satisfied, then A is called RS by module. Let's see the construct, drawing the diagram. When we consider if A is as a left R module, then this R product A goes to A. Okay, so we can consider choose in R A goes to RA. So RA clearly in element A, and because RA is in A, we can consider SB. In this case, it's A. Okay, this is the right S module. So because A is clearly in A, we can choose RA in A and S. Okay, then delete this. Then we can consider RAS goes to RAS. And however, in this case, consider in AS case, we can choose A in S in A product in S. We can consider AS goes to in A. Okay, so we consider A as RA goes to RA, AS goes to AS. So clearly AS is also in A. So we can consider RAS, then we goes to RAS. But not that. So we can see this is the property which generate left R module property. Okay, this mapping is made by left R module. And then we can consider this mapping is generated because by this is right S module. So the equation is in general does not hold, but if the equation is satisfied, then we can consider A is not only, in this case, A is not only left arm module, but also right arm module, if the equation is satisfied. Okay? This, guys, means this. RAS is the generated left arm module property, and this is the right arm module property. This equation means A is left arm module and as well as right S module. Anyway, this property holds, then A is RS by module. Now, let's consider the example of the RS by module. Just short, concise example is if R is a ring, then ring R is RR by module. This is clear because when you consider R to R, because all the notation is same, with this in C, this is pick R is the additive abelian group, then R is the left arm module, and C is the additive abelian group, then this is R is also right arm module. And when consider this property, if we choose R1, R2, R3 is equal to, by the ring property, associative rule. Also, this guy is also in R. So, R1, in this case, R2, R3 is also whole. So, anyway, ring R is the R by module. Now, I will introduce some theorism about the bi-module, but prior to this, I introduce some notation. Next theorism is the notation RA, small r, B, small s. This notation, what this notation means? If RA is given, then this A is a left R module. Left R module. Okay, and this RBS is, then B is by RS module. Okay, use notation. This is the notation. The theorism. Statement A is the home RAB's right arm module with the action of S given by here. This means here. Consider home RAB and S goes to S. In this case, home RAB. Then we consider map F and S goes to 2 Fs. But our claim is that home RAB is contained in here. So to do this, consider A. This is A. Then this is defined as the here. How to justification this? let's consider map fs is the A to B. Then I substitute the value of A. Then clearly to the well-defined fsa is contained in B. But this definition, by this definition, if this definition is applied, then this is clearly, we check this element is contained in B, then this definition clearly is well defined. To check this is easier because first f is in A, home A, B, so clearly fa is in B and S in S. But again, our assumption, because B is a S rightest module, this means we can consider S, B goes to B. So FA is in B, S in S, and FA S in B. So this is clearly in B, and this is well defined. Statement B is here. If phi is A to A is the homomorphism of the left R modules, then the induced map, this is clearly we defined in the previous lecture. This is homomorphism of R right RS modules. This means, and because this is the right RS module, we can check that we can check the two properties, this but in the multiplication case, we can, the notation, this is because of right S module, S is here, located here, and F is VFS. So in the case of the left arm modules, this link case is located left side, but this is the right side. This is the right RS modules. Let's prove the statement B. We can, the definition of the home set, we can easily check these properties. Remaining is the here. For phi fs is equal to phi s for all f is home R A B A prime B and S in S. How to prove this? In order to prove this, I'll copy this map and let's consider, choose fs goes to 2 phi fs. To well-define this, I use some notation A. Then because this is our home set, between the home set, by the definition, this map is clearly defined. Fs phi A. Using the diagram, directly check. Okay. Then this is written as F phi A S. Why this is written is here? By the here. because home RAB in this definition RS module, clearly home RAB in RS module, so FS, S is here, and in this case phi A instead of A. This is the definition is here. Check this property. And again, by the definition of the home set, we can also check directly using the diagram F phi F A S. Then for all A in A. So because for all A in A, this equation hold, we can say our desired result. Phi S. And similarly, we can get statement C and D, which is correspond to A, C, and B to D. Okay. Statement C is home RCD is the left RS module with the action of given S by this here. This means, in this case, home RCD, comparing to this statement, home RAB is right S module and home RCD is left R module. In this case, home RCD goes to home RCD. And if the map S and G is given, then S, G, but the additional notation C is required, and C, D is clearly, because SG, map SG is clearly home to be, in order to home CD, home RCD, C, this is SG, C, and SGC is clearly in D. Then this map GCS is well-defined map. In case of CS, because C is RS module, so in this case S, C goes to C, and CS goes to CS. So CS map is clearly in C. And the map G, what is the G? G is C to D. So this is clearly in C. This map goes to G, C, S in D. So this is clearly well defined. This from the SG is from the map spew out D. And similarly, we can check this is if the psi is homomorphism of left RS module. So in this case, we can, the additive property is clearly by the definition of the home between the home set, and this is left S module. Comparing to this is right RS module, this is left RS module. So remaining thing is to phi, if S is an element in S, is equal to this for S in S, and for all f home RCT. So comparing to this corresponding statement A to C, right and left is changed. So in this case, right R S module, this is left S module. Because, okay, this is right and this is left. And the statement comparing to B to D, this in this case, okay, left. This is right. This is right. This is left S module. And the comparing to map phi A to A prime, then this is goes through here, and the first rotation is A to A prime is located, and in this case the map psi is given. Then this is goes to D prime, and this is located second position. So now we are ready to study of the dual module. Prior to this, let's record the dual space in the linear algebra, and then compare the dual vector space in the linear algebra and the dual module in the module sense. Okay. The first comparing things, the linear map and the dual linear map, dual map. This is the dual map, dual space. We know the linear functional is here R, the linear map. And the linear map satisfies T and vector element in T, V and W rather than, I recommend the notation V prime is clearly T, V, T prime, and T alpha V is equal to alpha T V. Understand that this rather than item. This is good real number, field, or complex number. I recommend in this lecture put F instead of the R. Then how it comes from this alpha? Alpha comes from so-called scalar. Scalar is F, V to V. Alpha V goes to alpha V. This is clearly vector element. How about the dual vector spaces in the linear algebra? This is just a collection. The linear map, such the vector space from the real number is clearly linear functional. I said linear functional. So V star is the collection of the linear functional. But dual space satisfies some conditions. The first condition is when comparing to the linear map, the first condition is in this case, okay, T S V. In this case, the function satisfies T V S V. But this condition is clearly trivial. the definition of the sum of the function. And another condition is that alpha t v is equal to alpha t v for all element. So this is, then this two conditions satisfies, V is called dual vector space. Concept of the dual space on the linear algebra, we can easily understand the concept of the dual module. Okay, so let's read the definition of dual module. Let A be a left module of the ring R. Then home RAR is called dual module of A and denoted is A star. This is denoted A star. And note that when comparing to A is the left R module, but home RAR is the right R module. Previously, I showed that this is the right R module. Understand this theorism. Previously, we defined this statement. So we can understand that in this moment, home RAR is the right R module. R goes to home RAR. This is the right R module, and this is called dual module of A and is denoted A star. And each element is A star is called linear functional. As we said, this is functional. But this function we can understand f a. Okay, in the set notation, A star is the home RAR, means the collection of the dual morphism, collection of the R module homomorphism. In this case, left R module. So in this collection of this map, this is clearly when we consider if R is a division ring, and okay, the commutative property hold, then so this means R is the field so just R is the field, then we can understand the object A is the vector space. And we consider this linear map condition. Phi V W is equal to, and we can consider phi, in this case the R is the scalar, okay? Alpha V is equal to alpha V. So this is a linear map property satisfied. So we can generalization the dual module is generalization of the dual vector spaces. I want to say some remark on this some statements. Let's see when we see the dual vector spaces. That's the second properties. Why this second properties using? In this case, scalar alpha phi v is here. But note that when considering the definition of a dual module, so-called scalar in the right side, but in this case clearly left side. Why these problems happen? Of course, phi is clearly home AR. Clearly, phi is clearly in this statement B star, A star. But note that alpha is clearly in the scalar, so it's R, and phi goes to V, spew out value, but this is also R. So this is element, origin element in the ring element in R. Of course, when especially vector spaces are all scalar is a fit, so divisor ring commutative relation is clearly satisfied. Remarkable point, because the commutative relation satisfied, we can say this here, phi v alpha. And again, let's see the statement A. We can consider all corresponding, this is the statement. Phi is the home A in R, that's the statement A in R, and in the scalar, in this scalar, because okay, this is R, so the scalar, so-called scalar in ring R, and the web phi is the home RA in R, and this R ring R is specially commutative relation satisfies. Then anyway, because note that this property, anyway, to begin with, this is the commutative relations hold, and then by this here we can say this is alpha phi v. No, in this case by using this back, okay, this is alpha and phi v. Is no problem. Okay, then we can check phi alpha v, phi a v. This is alpha. Okay. Okay, then this equation goes to here. Then because the alpha goes to right side, so we can say this is no problem. But note that originally, so-called, this is generalization of a dual. This is good generalization of vector spaces. So all dual module is this right. The collection of the so-called this is the right R module. So scalar is originally located in the right side. But in the vector field, the case of the vector field, because this all ring is the commutative, so we run in the linear algebra the dual, so-called when we so-called dual spaces, the scalar is located in the left side. This is no problem. But when generalization of the dual module in the module sense, the scalar must located in the right side. Let's compare the dual basis with the vector spaces clearly have the basis, whether it is the finite or the infinite. But in this case, I'll consider the finite cases. This is the basis. And the number of the bases is the dimension. Number of bases. But in this case, I will consider the finite case. And if we consider the dimension, if the all vectors element in V is generated by linear combination, AI, EI, and this is clearly linearly independent. Linearly independent. And then consider the dual base. What is the basis of the dual vector spaces? In the dual vector spaces, the coordinate function is the basis. And the theorism, the number of the bases in the vector spaces is equal to the number of the dual bases. And the coordinate function means this is clearly in phi. So phi is the v into r. If v is the element in v, this is here. Consider here. Then when goes to here, this spew out the coordinate, I times coordinate. So the remarkable things, this is if we substitute in, okay, we can say basis is not, the method basis is not unique, but in this case, this setting, this is standard basis. Standard basis, then if we substitute standard basis in the coordinate function, this is index I, this is index j, this is index j, and this is index I. Then when we consider the definition of the coordinate function, this is 1 if I is only alive, I is equal to j, and otherwise is 0. Otherwise is 0. This property is important to understand the vectors, dual vector spaces. And then because this is the basis, we can understand all element in linear functional. To this, I will delete this condition. The theorism is dimension v is equal to dimension v star. And for all element in phi in the linear functional, is the generation by the dual basis element generation. So we can find the coefficients to bi by substituting e, j, as I said, bi, phi, I, ej. Then, as I said, only arrive I equal to j. So sum is already deleted, but when I is equal to j is arrived. So in this case, this is bi, it bj, Kronecker, I delta j. So well, as I said, as I already said, ei is 1 if I is equal to j, otherwise 0 is denoted Kronecker delta ij. This notation here, and this is bj because only I and j is equal. This values arrive. So we can find coefficient is bi or bj is here. So we can say phi is phi e I and phi I. In this case, let's compare the dual basis on the linear algebra and the dual module. So this theorism shows the able to compare the dual space on the vector space, dual vector spaces and dual module. So let F be a free-left module of the ring R with identity. Let X be a basis of each for each X in X. Let Fx this function given. What this means, in order to explain that, let's see the let F free-left module. We studied in the pre-module. F is given, then X is a basis, and then for any R module is given, this is the inclusion function. So for any R module is given, there exists homomorphism R module homomorphism phi such that the commutative relations satisfy. Then F is free left module. In this case, the homomorphism is left homomorphism. Because for any R module is satisfied this condition, I change this is R. Okay, then X is the basis and each in X. This map is well defined. Choose an element in Y. In this case, I substitute Y. This map is defined delta X Y. This means I said if X is equal to Y is 0, 1, and otherwise is spew out 0. If setting this Fx clearly, we can check home R XR. And because this is inclusion map, this is home R FR. Because X is the subset of F, this is contained in here. Okay, then I will not prove this statement, but just to check that the relation of the dual spaces in the linear algebra and the dual module. A, Fx is the linearly independent subset of F star with cardinalities X star. This is number of the bases or dimension or the length. So this means if we clearly has the basis that has finite basis in N, and this is the F is small subindex X is that means this F depends on the element of X. So if the number of the X is the N, then Fx is the number of the set has same number of the N. And this is a linearly independent subset of F star. This means the definition of the linearly independent statement, Fx1, but note that we can consider the this is the left R module homomorphism. Okay, this is the left R module homomorphism. Then I said the definition of the home RAR, right R module is the dual module is the right R module morphism. Right R module. Okay, right R module. So the R, the ring scalar, so scalar is located in the right side, and fx2 r2, so fxn rn is 0. If the definition of the independent, linearly independent, if this equation is satisfied, then Ri is 0 for all I. This is statement of A. And statement of B, if X is the finite, then, okay, if this cardinality is the whether finite or infinite, but are interested in only this finite case. So in this case, the X is the finite, then F star is the free R module with basis Fx. So if this condition is already linear independent condition, is the regardless of finite or infinite, okay? But in this case, if the condition is the finite, then it's indeed the basis. So this means F star is the home R fr. That's the pre-right R module with basis. Is generated by pre-right R module, and this means all element in home fr is generated by fx1 fxn. Looks like module is generated basis. This guy is also generated by this fx1 fx2 fxn. The dual map in the linear algebra and compare it to linear algebra and dual vector spaces. If in this case, if T is the linear map with two vector spaces between two vector space from V to W, we can consider the dual map, dual vector spaces from W star and V. How can we define this element? If this is where we define this, then we can define this dual vector spaces. But let's consider the W star means W goes to, this is a linear functional, so F goes to field. So if we choose the element in F in W star, then we can go this map from V star F. Then this is the T star F. Then the map is defined by easily guessing the commutative diagrams. Because this is map is well defined, so we can go to T, and F is the same, just rather than V F. So T star F is naturally well defined this by T composition F. So we can in the dual module we can understand the concept of the dual map in the module sense. So statement, I introduce statement A, B, C, but I will not prove this statement, just introduce the statement which is related to dual module. Okay, so let A, B, and C are left modules of a ring R. Then first, A is a dual map, so A to C is the homomorphism left R modules. Then the induced map C star to A star is the homomorphism of right R modules. Checkpoint is that the concept of the dual map, we can define the definition of the dual module is similar the dual vector spaces clearly, but the point is here. This left and right side is changed. So clearly we can check this is the well defined, but in order to check the homomorphism in the multiplication part, we must check that the coefficient, the scalar, so-called scalar, goes to right side. So this is here and equal to buff VFS. In order to multiplication property of the module, right R module, we should check scalar is to the right side. So okay, the second statement is show the properties of the exactly shows the dual properties. So if R is the divisor ring and this is the short exact sequence, because R is the divisor ring, we can consider A, B, C these objects as a vector spaces, left vector spaces. Then this is the short. If this holds, then this is the short exact sequence of right vector space. This is the important property to understand, to see the next in the future to understand the homology algebra. And we can see, even though we cannot prove this statement, we see the previous A or B's statement A or B is can proved by the previous theorism we are introduced. The lecture 6 mainly. The important point, this theorism shows frankly the duality property. Duality is always looks like image always the same but looks like a mirror. Okay, dual property, all of the dual is the word is dual is the well defined word, but when we observe all property about the duality, we can see that everything is the change, looks like a mirror. So in this case, this short exact sequence is the left vector, but this is the right vector, and this exact sequence goes to A, B, C, and this exact sequence goes inverse C prime, B prime, A prime. The statement C. This, if we try to write the precisely this here, so, but I recommend if someone try to prove this statement, this the general show that the generalization of the statement, and then using lemma prove this finish the proof of statement. What is the lemma? If AI, the index of the R module set, and B is also R module, then we can say this statement, this is isomorphic to this. But this is only satisfies in the finite index. So if we can prove this statement just n is equal, this is the case n equal to 2 and b is the r. So our proof is finished. Then if we try to this isomorphism relation, isomorphic relations easily, I don't know easily, but using this lemma, we can prove this isomorphism relation. This is I showed in the lecture 4, introduced in this statement in the lecture 4. So by using this lemma, by landing this lemma, we can prove this statement.